Good evening all. So I am going to start today the week 5 problem solving session. So in the week 5 lectures we studied about the so in the week 4 we studied about the precipitation hardening in 2000 series alloy, 6000, 7000 series alloys. So now today we will study about some specific alloy of 7x series and 8x series aluminum alloys. So in 7x series alloy, one alloy that is aluminum alloy 7050, which is generally used in fuselage of aircraft. Because this aluminum alloy is used because of its high strength to weight ratio. As the 7000 series alloy has high strength and the aluminum alloy already have low weight, so the specific strength of the 7000 series alloy will be much higher than the steel and other heavy alloys. So the 7050 alloy can be used in T7 condition that has good resistance. And in T6 condition. So the T6 condition 7050 alloy has low quench sensitivity. Low quench sensitivity studied in the last week about the 6000 series alloy. So low quench sensitivity means the alloy can be easily quenched from high processing temperature and there will be no solidification cracks because of the this cooling temperature gradient difference. So the 7050 alloy has the low quench sensitivity. Low quench sensitivity, and so that's why this alloy can be quenched easily and form super saturated solid solution all over the thickness of the component which has been quenched. Of thick forgings. And it can be quenched in hot or warm water also. The second alloy is aluminium 7005. which is used in T6 condition and generally used in automotive parts and ground transport. So next are the 8 series alloy, which is aluminium lithium alloy. So aluminium lithium alloy have some special properties, such as the lithium has lower density. So by addition of 1% lithium in aluminium, the alloy density can be reduced up to 3%. Sorry, up to 3%. So 1% lithium addition lead to alloy density decreases by 3%. So the aluminum lithium alloys became popular in the 1990s 80s because of their lightweight and high strength. So in the aluminum lithium alloy, the supersaturated solid solution directly forms the precipitate delta prime and delta. So delta prime composition is Al3Li and delta is the equilibrium phase, which has the composition of aluminium and lithium. So while the precipitates directly form from the supersaturated solid solution without the nucleation of GP zones. So in the aluminum lithium alloy, the activation energy to form the precipitate is very low, that helps in earlier nucleation of these precipitates. The precipitate, the delta prime and delta precipitates are formed ordered structure. So the strengthening in the 8000 series alloy comes from the ordered strengthening. Ordered structure means they have long range order. Similarly as seen in L12 structure. So the ordered structure has the crystal structure of L12. L12 crystal structure can also be found in copper gold system. That is the FCC crystal type lattice. So in the L12 structure of delta and delta prime, the misfit is very low. So the strengthening due to misfit between precipitate and the matrix is less significant in the 8000 series alloy, and the delta prime and delta precipitate have spherical shape. So how order strengthening happens in the 8000 series alloy? Ordered strengthening. So the delta prime and delta precipitates are shearable. type. Means as the dislocation moves through the precipitate, it shears out and form the extra form the surface that is the antiphase boundary. So the formation of antiphase boundary increases the applied stress for further deformation to continue, and thereby increasing the strength of the alloy. So due to the shearing of precipitate, the deformation is localized. So the localized deformation in the 8000 series alloy reduces the strain to fracture. Means EF, if we see the stress strain diagram, so this is called the strain to fracture. So this is very low in the 8000 series alloy. That's why aluminum lithium alloys are so the are not able has not been able to attain the much popularity after some time. And they started declining use in aerocraft and aerospace. Aerospace applications. And so the first this is for the delta prime. So the delta prime precipitate has the L12 structure, and delta which is equilibrium phase has the B32 crystal structure, which is found in sodium tantalum structure. Means in B32 structure, two diamond cubic lattices are interpenetrated. So some 8000 series alloy are, the first is the aluminum alloy 8091, which has the composition of aluminum, 2.6 lithium, 1.9 copper, 0.9 magnesium, and 0.12 zirconium. So zirconium are added to inhibit the grain growth. So in this 8091 alloy, delta prime precipitate composition is Al2CuMg. So this delta prime precipitate cannot sheared. Means this shear precipitate is not shearable. So one more thing, the 8000 series alloy has the less strain to fracture, and also the low fracture toughness. So in the 8091 alloy, the delta prime precipitate is not shearable, means it has some the strain is little high, but the fracture toughness could not be increased much as compared to the previous alloys. So this has the fracture toughness KIC value of 30 MPa and yield strength of 490 MPa. Gram per cc and the density. So the fracture toughness is very low while yield strength is very high. Second alloy 8000 series is 8090. So the 8090 alloy, the lithium and copper concentration is reduced. That lead to KIC increase in 40 MPa meter per square root of meter, and the yield strength is 430 MPa. So the 8090 alloy has the increase in fracture toughness, but this is still not required. That is not required up to the for aircraft applications. That's why it has the less application. So if we overview the precipitation hardening in the aluminum copper system, theta prime precipitate is responsible in increasing the hardness and strength of the alloy. So theta prime precipitate has the composition of CuAl2, and one more is Al2CuMg, which is S prime precipitate in different aluminum copper alloys. In aluminum magnesium silicon alloy, the precipitate are Mg2Si, in aluminum zinc magnesium 7000 series alloy has the neta prime precipitates, and the aluminum lithium alloy has the delta prime precipitates. So the strengthening mechanism like precipitation hardening and solid solution hardening is over in the heat treatable alloy. So what are the different strengthening mechanism in non-heat treatable alloys? So how the non-heat treatable alloy are strengthened? So first method is strain hardening. Non-heat treatable. First is strain hardening. So strain hardening is referred as the cold working or deformation at room temperature. So due to the cold working and deformation at room temperature, with increase in deformation, dislocation density also increases. So the increase in dislocation density increases the interaction between dislocations and its environment, increasing the applied stress required for further deformation. So in the strain hardening, example as rolling extrusion, as the component is rolled, the grain structure changes from the equiax to elongated. Means metal is deformed in certain direction. Like if the initial structure is like this, then the deformed structure will be this type of grains. The grains are deformed along a certain direction. So the strengthening formula is given for the strain hardening is given as sigma equals to sigma naught. So this is sigma naught A and this is sigma I plus alpha GB rho power 1 by 2. So sigma is the stress in the initial stage alloy, the sigma naught is directly proportional to density square root of dislocation density. Here G is the shear modulus, B is Berger vector, and alpha is the strain hardening coefficient. So as the dislocation density increases, the required stress is also increases, increasing the strength of the alloy. So the ductility in strain hardening decreases. Ductility is lower with strain hardening. So the increase in dislocation density is from 10 raised to power. So in the annealed crystal, means that is non-deformed, the dislocation density is 10 raised to power 4 to 10 raised to power 6 per millimeter square. That increase to 10 raised to power 10 per millimeter square in a deformed sample. So there is also a designation used for different types of strain hardened material. So if we see the temper name and condition. So in the strain hardened condition, first is the F. F represents the as fabricated. O is the annealed or recrystallized. Next is the H1. H is used for hardened component. So watch. So this can the condition of this is strain hardened. So in the H1 only, different types of nomenclature are found, like H12, which is followed by second digit, H12, H14, H16, H18. So H18 represents the full hardened. So the second digit in the H1 condition represents the degree of strain hardening in the alloy. So H12 is the 1/4, H14 is 1/2 strain hardened, H16 is 3/4 strain hardened, and H18 is full hardened. Next is the H19. H19 represents the extra hardened temper. Next is the H2 temper. H2 means strain hardened more than required, and partial annealed. So S2 temper also comes in different designation with second digit, H24, like S2, S22, H24, H26, H28. So the second digit in H2 strain hardened alloy shows the degree of strain hardening remaining after partial annealing. So the second digit shows the remaining hardening. Hardened phase. Next is the H3 hardening, so that is strain hardened and stabilized by annealing. H2 is strain hardened and partial annealed, where H3 is strain hardened and stabilized by annealing. Means the deformation is stabilized in this H3 condition. So in the H3, H3 2 and H3 4 temper also comes. That in the H3 2 and H3 4, the second digit represents the strain hardening remaining after stabilization. and the stabilization is done at 100 to 110 degrees Celsius. So how the strain hardening happens in the rolled or processed, like for after forming operation. So first is the lumbar coatal barrier. So how lumbar coatal barrier forms, as the if two dislocations are moving on two planes, this from here and this from here, so after meeting at a point here, they form a dislocation with a different Berger vector, like if this, and but that dislocation, if that resulting dislocation line is on non-closed planes, it cannot move or participate in the deformation process, and it become sessile. Sessile means locked, not able to move. So this is called the lumbar coatal lock. So with the, because of the formation of the sessile dislocation, further dislocation coming to this plane will agglomerate at the sessile dislocation, impose the stress and increases the strength further. Next is the formation of jogs and kings. This is lumbar coatal lock. Second is the formation of jogs and kings. So jogs are formed as the dislocation line interrupts. So if this is a dislocation, edge dislocation, and its Berger vector is in this direction. So and the line vector is in this direction. So it breaks along this plane. So the Berger vector is this, but so the Berger vector is in the out of plane. So jog is referred as the a step formed in the dislocation line out of this original slip plane. So if this step is out of the slip plane, is called the jog, and if it is in the plane, then it will call as known as kink. So with the different interaction between screw dislocation, edge dislocation, so with the edge dislocation interaction, two kinks are formed. Like if we see the dislocation, coming in this line, it's coming to this side. This has the Berger vector V2 and this has the V1, but it is moving in the opposite direction of V2. Second, this is first and this is second dislocation. So after intersection of dislocation, the dislocation line form a kink So this step is in the similar original plane of the both this location. So for first dislocation it is in this plane, while for second dislocation it is in this plane. So the Berger vector will not change. If Berger vector is in this direction, it will be this and this, and line vector is also comes to this. So this this will form a screw kink of the screw nature, because Berger vector and line vector is in the same direction and with 0° angle. Similarly for this also, this is Berger vector and this is line vector. So this will also form kink. While in the case of screw dislocation, if two screw dislocation are forming intersecting B1 and B2, after the intersection, a step after the slip plane for screw dislocation are formed. So this is B2 and this is line vector. Similarly, this is B1 and this is line vector. So these formed are jogs of H character, because the Berger vector and line vector are perpendicular to each other in this case. So in the edge dislocation intersection case, the steps are in the original slip plane and they can glide freely as they line in the slip planes of the original dislocation. Means the step formed in the two edge dislocation interaction are glissile nature. Glissile means can be easily moved, can move freely. While for the screw dislocation interaction, a jog edge character form which is sessile in nature, means cannot move. So different type of interaction happens during strain hardening. First is one is the sessile lock. Second is the interpenetrating slip planes. Interpenetrating slip planes can also inhibit the dislocation motion. Third is strain hardening, because of the strain fields around dislocation. So the strain hardening process, how the microstructure will look like. So the cold work structure has the elongated grains, and after further deformation, if deformation is high, then dislocation cells form that are called substructures. Cellular substructure means in a alloy. The cellular substructure are formed. The boundaries of these cellular substructures have the dislocation tangles of high density. So the formation of cellular substructure depends on the different parameters as the material. So how the material is formed, like if material can be easily deformed, then dislocation cellular substructure form readily and increasing the strength significantly. So if this material is hard, then the formation of cellular substructure is also difficult. Second is the strain. With increasing strain, the cellular substructure in formation increases. Second is the strain rate. So if strain rate is high, then the formation of cellular substructure is more favored. Then temperature of deformation. At a low temperature, the development of cell structure is less dominant. If temperature is low, then cell structure will form very slowly or after a very long time. At high temperature, dislocation has the activation energy to cross the barrier that further participates in the deformation process and increasing the dislocation density further. And it is also true for low stacking fault energy material. Means if low stacking fault energy is low, then the dislocation moment will be hampered and the formation of cellular substructure will be low, will be less favored. Which with low stacking fault energy, low cross slip will happen. So if the dislocation cannot cross slip, deformation will be restricted and the substructure will not form. One more thing, that at high strain rate, this phenomena is also less pronounced, means the structure will not form. Next is the pile up of dislocation. As the deformation proceeds, this is grain boundaries, then dislocation comes to the grain boundary and it cannot move because the orientation changes from this grain boundary to this. So if the slip plane is this, in the second grain boundary the this slip plane is this. So dislocation cannot move freely, cannot go to the second grain, imposing. So the pile up of the dislocation create a back stress that cancels out some amount of applied stress. So further deformation, higher stress is needed to apply. Thereby increasing the strength. So if pile up can occur over a long range also. Pile up can occur long range also. Next is the annealing process. So after strain hardening, and the strengthening mechanism contains the annealing. Annealing is due to annealing, various properties are increased and some properties are decreased. Like for these are the annealing is the restoration of ductility and electrical conductivity in the alloy, strain hardened alloy. So annealing is the heating of the strain hardened material at a high temperature for certain time. Period. After heating and holding at a certain time, for a certain time, the cooling happens in the different medium. Like if cooling is done in furnace only, inside furnace, then it is called the annealing. If cooling is in air, the rate of the cooling of the annealed material is high, means rate is increases, so this is called normalizing process. So this can be done in air or forced air cooling. So in the annealing process, dislocation density increases. So how the dislocation density is reduced in annealing? So first method is the annihilation and elimination of dislocation. Means elimination. In elimination, the dislocation comes at the grain boundaries and fills the irregularities and disappearing at the grain boundaries or free surfaces. At free surfaces, they create a step. So annealing has the different stages. First is the recovery and recrystallization. So in the recovery process, so the recovery is the initial stage and recrystallization is the second stage of the annealing process. So in recovery, mechanical properties are not decreased, are not affected much, but the recovery increases the electrical conductivity of the deformed material. So how the electrical conductivity is increased in the annealing process? During recovery, vacancy concentration got decreased and vacancies and defects concentration decrease. So the decrease in vacancy and defect concentration allows the electron to move freely without any hindrance, thereby increasing the electrical conductivity. Vacancy defects, point defects. Second is the annihilation of dislocation. Like on a plane, if one dislocation is of positive sign, second dislocation is of negative sign. If they come to each other, then they will annihilate. So this represents the first extra half plane. This will represents the extra half plane at the bottom of the slip plane. So after coming to each other, they form a single plane, that is long range, and that annihilate the dislocation by formation of a new plane. If dislocations are of same sign, then they will repel each other. Only the opposite sign dislocation can annihilate. So what happens if the dislocation of same signs come together? So next process is the first is the annihilation of dislocation, second is the polygonization. No, polygonization will come later. So the same sign dislocation arrange in a array, in a vertical array, forming the low grain boundary low energy grain boundaries. That are generally called tilt boundary. Second process is polygonization. So in the strain hardened material, the dislocation are of this type. On different planes dislocations are. So after a recovery process, they arrange in a one manner like this type. So this process is called polygonization. And due to the polygonization, energy of the material, strain hardened material, got reduced. This of high energy, low energy. So the material is stabilized in this condition. Next process, so this is the recovery process in which dislocation density decreases and electrical conductivity increases because less scattering points are there after the recovery process. Second stage in annealing is the recrystallization. Recrystallization is the formation of strain-free grains. So how the strain-free grains form? If we see in the polygonization process, dislocation are rearranged in some array on the different slip planes, and the regions which has the low dislocation density acts as a strain-free nucleus. So that this strain-free nucleus further grow and form the strain-free grains. So the recrystallization can also can only be happen in the high stacking fault energy, high stacking fault energy materials. So how stacking fault energy attribute to the recrystallization process? If we see in a dislocation loop, this is dislocation loop, Berger vector is in this side. So if we see the line vector along the loop, so in this direction line vector is this, which is parallel to the Berger vector. So here it will be screw character, while it is at this point T will be perpendicular, this will be parallel, and this will be perpendicular. So at this edges the dislocation are of H character, and for these edges the dislocation is of screw character. So if it move from the one plane to other, means dislocation is moving from this point. So after coming to this point cannot move, but this can increase. No, this cannot move, this can increase. So it will come as this can increase, and it will cross again double cross slip on the similar slip plane. If it is 1 1 1, this plane will be another 1 1 1 type. Then it will come on this similar, on the same slip plane after the double cross slip. So the tendency to cross slip of dislocation helps in the recrystallization process. Means if stacking fault energy is high, recrystallization will be easy. While for low stacking fault energy material, the recrystallization is difficult. So the recrystallization depends on different factors. First is if it requires a minimum amount of deformation. Means the component should have the some deformation in it that enables the recrystallization. So how the present deformation helps in the recrystallization process. The strained material has some strain energy stored in it. That strain energy helps during the recrystallization process. Second, so minimum amount of deformation is needed. Second is if degree of deformation is higher, then the temperature needed for recrystallization will be low. Means recrystallization will start at lower temperature only. Third is the annealing time increase. If annealing time is increased, then recrystallization temperature will be low. Next is the grain size after recrystallization depends on the degree of deformation. Means as the degree of deformation is higher, grain size will be small, of the strain recrystallized microstructure. Also, the greater degree of deformation and lower temperature, the smaller the grain size, and low temperature will result in finer grain size. Finer grains after recrystallization. Fifth point is if the grain size of original initial product is larger, the greater amount of cold work will need that produce to produce the equivalent recrystallization temperature. If initial grain size is large, then temperature we should have to increase to achieve the recrystallization. If the material is of high purity, then recrystallization temperature will be low. If purity increases, purity of material is high, if the working temperature is high, then amount of deformation also have to increase. To achieve the recrystallization temperature. Means if working temperature is high, then amount of deformation should be given very high to achieve the same recrystallization temperature with the low working temperature condition. So as we see in the recovery process, annihilation of dislocation. While for recrystallization, the amount of deformation is important. So as the amount of deformation is high, then the strain energy stored in the material will be high. This strain energy helps in recrystallization process. Releases during recrystallization. So if we want to compare two samples, one which is cold worked, second is annealed. So how can we distinguish between two samples if we do not know their working processing history? So one method is differential scanning calorimetry. So in DSC, the temperature flow is analyzed. Temperature flow in the material is analyzed. So this is the heat flow. Heat flow. This is positive. This is high. So this will show the exothermic reaction. This will see the endothermic, means its energy is absorbed, while for in this below portion the energies are released by the material. So this decrease in the heat flow during heating of the material. This portion shows the release of strain energy. So during the recrystallization process, if we plot a diagram between power input and temperature increase. So the power input increases and then decreases. So this process is called the recovery process, means power input is increasing. At the point where occurrence of recrystallization starts, the decrease in power input happens because of the release of strain energy that helps in the recrystallization process. In this portion, the power input is decreased. So the recrystallization is the formation of strain-free grains. So how the formation of strain-free grains happen in the recrystallization. So first method can be during the polygonization. So in the polygonization method, if dislocation is arranged in a manner, so this area and this area is the free. And there is no strain in these areas, strain free. These strain free areas, the regions act as nucleus, and after reaching some critical size, if the strain free region reaches a critical size, form strain free nuclei of grain. That nuclei will grow and form the recrystallized microstructure. Second is the strained grain. Like if we see the two grains A and B, which this is the low strain, this is high strain. So there is energy gradient present at this green boundary. Due to the energy gradient, the low energy region boundary start to bulge into the high strain boundary. This bulging leads to nucleus of strain free grains. Next is the subgrain formation. This happens because by the rotation of grains that are adjacent to each other. Like if we see the two grains, so this is the rotation. So after rotation, this will form. So this is the interface between each other. Removing the interface between each other, forming a single grain. If the orientation is this in this grain boundary, after the rotation, the arrangement will be of this type, same. So this is the overview of the week 5 lectures. We will meet in the next week for the week 6 problem solving session. If today nobody maybe nobody are able to join the session. If you have any doubt, you can post in the discussion forum. I will reply to there also. Thank you.